Welcome back to Piste Perfect Ski Resort Builder. The big change this month has been the development of the Continuum crowd-field system to handle the pathfinding AI throughout the resort. This marks a significant step up from the simplistic graph network we were using previously and was implemented from scratch using the 2006 paper linked below. This video will take a retrospective look at the journey I took building the system, with a mixture of high-level concepts and coding details. As well as the crowd-field model itself, some of the tools I used were new to me, and it's valuable to reflect on this process. I'll start by outlining why I built the system, then cover the development of an initial working prototype in C++, before discussing optimizations using ISPC to write SIMD versions of data transformations. The system is still a work in progress, so I'll close by considering what the next steps will be for its development. For me, one of the hardest parts of software development is knowing when to use tools that others have already made and when you need to make your own. Even after nearly a year working on this project, my own codebase is less than 3% of the total code from the Unreal Engine and other plugins I'm using. Unreal Engine comes with significant modules for pathfinding built in. Why did I make my own? The two main questions for me concerning build versus adopt are discoverability and fitness for use case. By discoverability, I mean how easy is it for me to find the off-the-shelf tool, and how easily can I learn what its knobs and levers are? On the whole, Unreal Engine tends to do okay at this. It has a huge community and active Discord. It isn't hard to search for several built-in systems that cater to AI navigation, e.g. the navigation mesh system and AI agents. Video demos are easy to find for most things, especially anything with a heavily featured blueprint interface. Once you find some candidate tools, fitness is the question, does a tool meet your table stakes? The three salient features we need for pathfinding in Piste Perfect are support for large numbers of agents, i.e. thousands, runtime player-driven modification to the navigable terrain, and appropriate handling of the wide height range that the agents move over, at speeds much faster than walking or running. While the large numbers requirement is increasingly common in Unreal projects via the Mass Entity plugin, landscape modification remains a rarity, and most game environments cater for walking or running style movement. So going in eyes open, I was expecting that at a minimum I would be taking any native tools off Piste. Within a few weeks of working on Piste Perfect, it was clear that the core simulation would need to run through Mass Entity. Having followed through Mass's version of Hello World, see the link in the description, I was initially optimistic that the native movement processors could get the job done. However, that optimism was short-lived. Ski slopes are really quite different from pavements, and skiers are not pedestrians. While a city is, to a good approximation, 2D from the agent's perspective, a ski resort is not. I settled for a functionally sufficient pathfinding model that focused on the simplest element around which we could build the other systems. A directed graph connecting lift inputs and outputs of pistes so that guests could circulate the resort as it evolves in real time. A fixed velocity pointed at the next target node, and a shared brute force lookup table for assigning trajectories isn't pretty, but it got our ski boots strapped. 9 months into the project, and enough mountains had been moved that the skiers were looking mostly artificial with very little intelligence as they floated mechanically across the dynamic voxel plugin landscape. In September and October, the focus had been on polishing the look and feel of the core building systems. By November, like waiting to catch the first chairlift the morning after a heavy snowfall, the momentum felt right to take on a significant new feature, one that would enrich the simulation emerging from our mountain diorama. The next best thing to using a plugin or module that somebody already built is using their mathematical model. Continuum crowd fields are a well-proven approach for amortizing the cost of pathfinding in a simulation comprising thousands of entities. The seminal research paper that I followed was originally published in 2006, and I also gained a lot of implicit help from an interview with one of the developers from the Planet Coaster team. Links for both of those are below. Anyone dipping their toes in the algorithmic pool of computer science will come across Big O notation, which measures how the running time of an algorithm scales relative to how many elements that algorithm is running on. If we're to simulate thousands of entities, and we run our pathfinding algorithm per entity, then regardless how good that algorithm is, we take that number and we multiply it by thousands. In gaming terms, your budget per frame at 60 frames per second is 16 milliseconds. If we want to compute 1,000 entities paths within this budget, then we're effectively dividing that budget by 1,000, so we only have 17 microseconds per entity. More entities, even less time per entity. A modern 4 GHz CPU completes about 68,000 cycles in 17 microseconds. So depending on how complex your graph topology is, that might look like enough. However, there are two big elephants in the room. One, the number of goals is significantly less than the number of entities, so we will be repeating a very large amount of work if we solve each entity's pathfinding in isolation. Two, the field of movement available to each entity is influenced by the position and velocity of every other entity, since they also want to avoid each other. In big O terms, that's an n² amount of work that will explode our pathfinding budget as the entity count increases. We'll take another look at the wide timescales computers work across when we consider optimization. The central conceit of a continuum crowd field is to treat the entities like particles carried, sometimes called advected, by a universal flow towards a shared set of goals. For 1,000 entities heading to any of 5 goals, instead of computing 1,000 paths, you would compute 5 fields, one for each goal. If the goals are fungible, you could even compute a single field, and let the particles simply advect towards the nearest. If the number of entities is small, then it's possible this approach is less efficient than directly handling each entity. But the entire point of adopting a continuum crowd model is to support large numbers of entities. Trade-offer accepted. Although we want to model a continuous field, we need a discrete grid for computing an approximate solution, and this requires picking a scale at which to quantize. The final particle behavior can interpolate between the nearest set of grid coordinates, so the movement isn't restricted to axial grid directions or units, but we still face a trade-off between the precision of the cost field result and the time taken to solve it. 1 meter is a neat starting point, both mathematically convenient and a scale that loosely approximates personal space in a crowd. With a 1 meter grid size as a plausible starting point, we need to do some back-of-an-envelope maths to decide how we're going to rasterize and store the grid data. 8 kilometers by 8 kilometers is an ample-sized landscape for open-world building sims. For example, Satisfactory, which also runs on the Unreal Engine, has a map roughly 8 kilometers by 7 kilometers, of which about 30 square kilometers is buildable space. Hence, an integer coordinate system of 8192 by 8192 is more than we're ever going to need. That's equivalent to an 8K texture, but we'll need several layers for the different sets of variables. Ideally, we want to have a paging system that allows us to store only the areas in use. We split the global coordinates of 2 to the 13 cells per axis into 2 tiers of handles. A tile handle with dimensions 512 by 512, and a cell handle comprising a local coordinate in a tile's 16 by 16 grid, plus a tile handle. Using this split, we can get away with only storing the tiles that are currently needed by the system. The tile handle allows lookup into a statically sized array of the actual indices for the live tiles, which are themselves stored in a dynamic array. Thus, cell and tile handles are stable, tied to the global coordinate. Whenever accessing the live tiles, an ephemeral cell or tile index can be created as a temporarily validated token. Having sketched out a storage concept and scale, the next step in understanding the algorithm was to read through the paper several dozen times and pull out a list of all the variables needed to solve the field. The shape of the algorithm still wasn't completely clear to me, but I took a stab at organizing the data and made 2 structs. One for the variables that were definitely shared across all users of the system. That's terrain height, terrain speeds, north, south, east and west, average density, average velocity x and y, max field speeds, north, south, east and west, and discomfort. And another that would be dependent on the specifics of an entity group, e.g. which goal they're moving towards. Per-faced cost deltas, north, south, east and west, cost potential, cost gradient x and y, and finally, field velocity x and y. I knew this division was too simple and would probably cost me some later work, but you can't put up a building without raising some scaffolding. Designing systems is similar. It's valid to accept a naive solution initially as a stepping stone. A fat struct has the advantage of focusing all the algorithm work onto a single crossroads. You visit that crossroads enough times, and maybe you learn some shortcuts. Now that I had some data types to pass around, I could get to work translating the paper's description of their algorithms into C++ code. The crowd splatting section seemed like a good place to start, because it didn't call on too many different variables and would get me visualizing how continuous data ranges map onto this quantized grid. The next week of work was a fairly steady cycle of adding a new operation from the model's pipeline, setting up some tests to verify that my code was doing what I expected, and tidying up how I was organizing each part of the system. Writing unit tests is something that LLMs deliver high value for me. Hand over the files that need testing, give some surrounding context and maybe a previous test suite for style, and you're guaranteed to learn something useful about your code. The worst case scenario here is that the LLM writes a test that does what you request, and your code passes. Anything else is a valuable exercise in either locating bugs in your core code, or focusing the prompt, aka improving your explanation, and iterating the test suite. The highest cost I've found from working like this is that with only a limited context window, the LLM is often happy writing verbosely repetitious code, instead of building a library of test helpers that apply across several similar suites. I did encounter some painful refactoring episodes, where old tests were no longer applicable because the types had changed. Updating the tests was sometimes worth the effort, but sometimes it was simpler to generate new tests. As the test suites grew in number, I took effort myself to grow the surrounding infrastructure of test helper functions. This provided clearer prompt context, and the cost of replacing tests when I needed to make more invasive layout changes became less of an issue. The critical thing was to at least maintain a window of tests that bridged each addition or refactor, so I could be sure I was making progress, not just spaghetti. It took about 10 days' work to get a minimal round-trip pipeline of the crowd-field system. The particles advected by the system are hosted by the mass entity system. The overall hierarchy of data updates in the simulation looks roughly like this. The latest crowd data is pushed from the mass side once per frame after the particle locations update. The terrain updates are pushed by the buildable system whenever a player modifies the game world with features that add or remove navigable topography, e.g. pistes or lifts. When either of these tasks completes, the tile arena increments its data version. The shared fragment responsible for accessing the simulation can thus see when its field velocity tiles are stale and request an update. This creates 3 core buffers for the simulation. 1. Terrain data. 2. Crowd particle data. 3. Requests for updated velocity fields. The architecture separates the work into layers. The core crowd field simulation is a synchronous wrapper around the data layouts and internally calls free functions to carry out the details of each update type. This is hosted by the crowd field context, which manages the task scheduling. It ensures that only a single update type is happening at once, balancing the alternation of terrain, particle data, and velocity field requests. The context buffers its incoming data, and a separate read-only copy of the tile arena index is made for use by the outgoing field velocities. The particles thus have a valid field available even when the next update is in flight. When the context finishes this next update, the pointer is swapped before the next frame of velocity reads. It took another 10 days further work from beginning the mass entity integration to seeing a plausible-looking crowd of skiers flowing down the pistes. The raw output from the model paper's design turns out to be a pretty poor fit for skiers. The scalar cost field solved via the iconal quadratic relies on a stateless particle model, i.e. no momentum per particle. This is a key assumption that the authors highlight. At every update, particles immediately set their velocity to that given by the field at their location. Computing a cost field that accounts for particles' momentum is not feasible for a real-time context. The use of anisotropic velocities is a powerful compromise, as it can model the relative ease of moving downhill versus uphill, but trying to account for different entry velocities breaks the core premise of the overall approach. We can no longer assign a single cost goal for every cell, and no longer solve on the basis of a strict heap-based global ordering. However, we can achieve a more plausible-looking simulation by allowing particles to treat the velocity field as a target and gently clamping the acceleration to that target. Since skiers accelerate by falling, 9.8 meters per second squared, i.e. 1g, is an effective upper bound for acceleration, and 3.5g for deceleration roughly matches what a competent skier might experience. After a couple more days tinkering with stylistic code improvements, it was time to try out a new toy. Through using the Voxel plugin, I'd come across the ISPC language as a far friendlier way of writing SIMD code than learning platform-specific intrinsics. The data-heavy structure of array crowd field pipeline seemed like a perfect candidate for learning how to use ISPC, and I already had a fully functioning vanilla C++ implementation to act as a baseline for numerical correctness. I cannot stress enough how badly I would have lost my mind if I'd tried to code the ISPC version from scratch. I've only been writing C++ for about a year, and the idea that if you happen to own the adjacent memory, you can scribble whatever nonsense across your data, like a toddler armed with crayons and their parents' tax returns, is both terrifying and hilarious. I was much less amused to find that JetBrains don't have any support for ISPC. VS Code sort of came to the rescue, but the weaker refactoring tools and syntax parsing made for a real uphill struggle. Compared with learning Java, TypeScript, SQL, or even C++, ISPC is hard because the tooling isn't there. I decided to fall back to the simplest tools that I know work. Each kernel essentially comprises some pointer maths to make a stencil, and a core function called for each data payload. A common bit of advice when writing functions is avoid adjacent parameters with identical types. Such a design makes it easy to accidentally pass arguments in the wrong order, resulting in garbage at best, undefined behavior or crashes at worst. Sometimes though, there's no point in trying to hide the fact that you need 5 parameters, of which 4 are float arrays, all the same length. That's where my baseline C++ implementation and unit tests prove their value. Once the plumbing outside the ISPC kernel is hooked up, we can use C++ abstractions to safeguard future code from sending the data down the wrong pipes. After working through one cardinal direction of the cost per face computation, I found that the easiest way to work with ISPC was by first writing up an example implementation and then wrapping blocks of code in macros. I could then compose the variants for each other cardinal direction by stitching together the pointer arithmetic and the macro blocks. It's not my favourite code I've ever written, but the approach gave me the flexibility and deduplication I needed to convert and debug all the embarrassingly parallel sections of the tile data pipeline. If you ask an experienced software developer a question like, what do you think will be faster, A or B? You'll most often hear the response, don't guess, profile. Computer science is inherently a very empirical science. The measurable outcome of a system is what matters, not a theoretical or aesthetic argument for something. I have 2 main perspectives on why this is. Firstly, computers are an abstraction tower. Every element of their design serves the same goal: make it easier for humans to process data without thinking about the route electrons are taking from a plug socket to a circuit board and back again. Every level of abstraction is intended to simplify our interactions with computers, both as users and designers. Model the things we expect and need to change. Try to ignore the things we consider irrelevant. These abstractions are also necessary. A single human could no more design and build a modern computer system from the silicon to the operating system, any more than they could erect Stonehenge. The abstractions allow us to compartmentalize or encapsulate, as software engineers often say, and thus work on only the part of the system that we are currently interested in. The trade-off for abstraction is that we accept a certain amount of ignorance about the parts of the system we're not working on. The ignorance might be somewhat temporary. We may in fact have a deep and detailed knowledge of nearly all of the system we're developing, but it's nonetheless necessary and inevitable to focus our context window on the immediate frontier. Good peripheral vision for the design context will lead to a more predictable outcome, but we have to reserve certainty for those things we've empirically confirmed. Secondly, and related to the abstraction tower, there is a timescale tower several orders of magnitude high. Humans gravitate towards feeling a musical pulse in the range 60 to 240 beats per minute. Tempi outside this range will be felt more naturally in double or half time. That means we like a beat that's not longer than a second and not shorter than a quarter of a second, or 250 milliseconds. The classic frame rate of cinema is 24 frames per second. Slower than this, and the motion is no longer smooth. That's about 42 milliseconds. As we touched on earlier, most modern games aim for 60 frames per second, or a frame budget of about 16 milliseconds if we round down. Modern CPUs tend to run at around 4 GHz, meaning one processing cycle lasts about 0.25 nanoseconds, and a frame spans about 67 million cycles. This means it's entirely possible that we could optimize a task that runs once a frame and make it 100 times faster, and it might not actually visibly impact the game performance. How could that be? If the task previously took 700,000 cycles, it now takes 7,000 cycles, saving 693,000 cycles. If we're hovering around the 67 million cycle budget, that might free up just enough time to keep the frame rate smooth. On the other hand, if we're lagging at 30 frames per second, taking 134 million cycles to complete a frame, we're hardly moving the needle if we reduce it to 133 million cycles. I recommend the Computerphile video linked below for a longer look at computing timescales. All that said, I was pretty chuffed when my benchmarks showed that versus the single-threaded scalar implementation of the same computations, the ISPC versions, batched across 8 parallel tasks, showed between 30 times and 100 times better performance, depending on the computation being parallelized. Happily, these gains were also meaningful in context. The slow versions were taking several milliseconds, corresponding to a significant chunk of the frame budget, meaning the fast versions were now cheap. While 100 times performance improvement might seem pretty wild, it's not actually difficult to explain. The fast version has 2 core parallel aspects. The ISPC implementation is doing 8-wide SIMD. SIMD stands for Single Instruction Multiple Data. In other words, on a single CPU core, it can load data in gangs of 8 and do the same operation simultaneously to each instance or lane in the gang, i.e. it stands a good chance of being immediately 8 times faster. That's still only on a single CPU core. At a higher level, the fast version also splits the overall work into 8 batches of tiles, launching a separate task for each batch. Provided there are at least 8 logical cores available, we can theoretically get another 8 times performance boost. That's 8 times 8, i.e. 64 times as much data getting processed at once. If we can just get a 2 times improvement across the overall design, our theoretical ceiling becomes 128 times faster. That last 2 times comes from the design choices that SIMD code nudges you towards. I wrote the slow C++ version to make it easy for myself to read and understand my own code. Each cell in the grid is processed as a distinct input. The cell handle provides convenience methods for looking up the cardinal neighbors, and all the different computations use a single templated abstraction that branches per cell depending on whether a desired neighbor cell is available or not. In contrast, the ISPC version branches per tile, i.e. 256 cells, to determine whether boundary cells can look up a real neighbor tile's data or whether to pad that kernel call with a sentinel array. Execution branching, like in the per cell version, is slow because it makes the data access hard to predict, and therefore hard for the CPU to load data before the exact moment it's needed. The ISPC version eliminates literally hundreds of execution branches per tile. Combined with the 8-wide SIMD and 8-wide task batching, reducing execution branching sees us comfortably over the 100x finish line. The core performance multiplier ISPC leverages is parallel processing. Some of the improvements I achieved were linked to other optimizations, but this is the core tool. Parallel computing rests on a core premise, that the result of each operation is not dependent on the result of any other operation. For big chunks of the crowd-field pipeline, this is true in the best possible sense. For the thousands of cells we need to process, each only depends on a shared pool of input values, not on the output value for any other cell. This is the data dependency hierarchy again, with the parallel computations shaded in blue. The odd node out is the I-kernel cost potential solver, in red. The model implementation uses a heap-based fast marching algorithm. This relies on the opposite premise to parallel computing. The cost potential of any cell is strictly dependent on its upwind neighbors, i.e. those with lower cost, nearer the goal cell. The heap queue ensures that every cell is processed in this strict order, and thus the correctness of the final result. This is the bottleneck, the rate-limiting step in the pipeline. Even with an unlimited number of cores, allowing us to process the blue nodes nearly instantaneously, we can never round-trip this pipeline faster than the red node. The big O for the red node is n log n, where n is the number of cells. Bottom line, as we increase the number of grid cells in our field, we get a slightly worse than linear growth in the running time for that task. However, there are alternatives to the fast marching method. The fast marching method treats the problem as a wavefront, starting from the goal cells and expanding outwards, always accepting the single next lowest cost potential cell as stable. By contrast, a sweeping approach picks an axis and, along an orthogonal axis, treats those cells as independent, processing them in parallel. Because this approach does not respect the strict ordering premise like the fast marching method does, it requires multiple passes in different directions to converge on the true cost potentials. It also requires some degree of coarse-grained sorting in order to be effective. the cost potentials must still propagate from the vicinity of goal cells outwards. In terms of our model, processing tiles distantly connected to the goals is meaningless until the wavefront has reached their neighbours. A simple way to implement this is to keep an atomic for each tile, tracking its awake state. During each pass, if a tile is asleep, we skip it. If any of the tile's cells updated in that pass, we wake this tile up again for the next pass, plus its neighbours. During the first pass, we wake up all the tiles containing goal cells. The algorithm terminates when no tiles are awake. In my test run, for a 32 by 32 tile arena, starting with a single goal cell and randomised heights, the sweeping algorithm took about 200 milliseconds versus about 500 milliseconds for the marching algorithm. However, there's a slight catch. The marching algorithm is only serial per goal set, whereas the sweeping algorithm is already parallel for only a single goal. If you're wondering why that's a negative, consider if we had 8 different goal sets needing unique velocity fields. For the marching approach, these could run in 8 parallel threads, still taking about 500 milliseconds for the test scenario. The sweeping algorithm is already using parallel thread bandwidth, so we may not be able to run any extra goal sets in parallel. The 8 goal sets could take as long as 1600 milliseconds. There was a final twist to this comparison. I was still running in debug mode, meaning the compiler was not optimizing as aggressively. So I went to test in a shipping build, and the sweeping algorithm broke entirely. This cost me about a full day trying to understand why, and as far as I could determine, the error was not in fact mine. Somewhere in the code generated by either the ISPC compiler or the Unreal Engine's tooling for ISPC, my function that was supposed to return a strict bool type was returning something else, seemingly a vector mask that should have been converted to a bool. The C++ side of the call was operating on the contract that the type was a bool, and in shipping builds, the compiler optimized this by storing the return directly in my enum variable, the type of which also had only 2 possible values, and was size unsigned int 8. I figured this out very slowly, adding increasingly aggressive sanity calls to verify values. Eventually, my enum variable failed to verify, asserting that its value was any of the only 2 defined members of that enum. Huge red flag. The minimum solution that could dissuade the compiler from optimizing via its faulty contract was making the function return one of 2 const expr variables, assigned to the 2 enum values. It was a Pyrrhic victory, however, because in shipping builds, the marching algorithm turned out to be twice as fast as the sweeping algorithm, and 4 times faster than itself in debug builds, so the fast marching method remains the active implementation. Content that all the obvious optimizations were done for the system's core pipeline, there were some visual improvements needing to be made. Although the particles' movements were restricted to within the navigable area created by building pistes, no obstacles could be added. I fixed this by adding a simple routine for drawing polylines across the 2D raster used for the navigation grid. I also added an actor that could read from the current tile arena and create decal components covering the tiles active in the arena. Aesthetically basic, it shows green for navigable and red for unnavigable, making it easier to spot a few more bugs and experiment with restricting the particles' movements. There was still one aspect of the velocity field that was distractingly janky. When areas around goals became congested, the gradients, and therefore velocity headings, would begin to fluctuate at high velocity. In successive updates, an area would be blocked, causing the crowd to move away, and in the subsequent update, the alleviation of this blockage would flip the polarity back to its original gradient. This manifested visibly as jittery movement, oscillating rapidly between 2 competing headings. To reduce this, I added temporal smoothing when updating the field velocities, using a logistic curve to interpolate between the previous field and a new one, based on the delta time since the last update. The system is in a pretty good place for the 8 weeks since I began working on it, but it is still a long way from finished. At present, the tile arena is treated by the solver as a single blob. While this is fine as an initial design, a realistic navigation grid is likely to have concave regions that can be partitioned into connected components. This would make it possible to split the problem into a series of dependencies at a higher level. After all the cells along an interface between 2 components have been accepted, an additional solver could begin in parallel, working on this isolated component, beginning with the interface as the initial wavefront. While determining suitable component partitions and triggering the secondary solvers would not be a trivial extension, It could offer significant gains in terms of breaking the serial bottleneck and improving cache locality within each solver. Each velocity field assumes that the goal cells, set to cost 0 at the beginning of the solving phase, are fungible. Particles cannot express a preference for any particular goal cell initialized for this solution. They simply advect down the gradient along the cheapest path to any goal. This higher level preference is modeled by solving multiple fields, initialized with different goal cells. As highlighted when discussing the sweeping algorithm, these fields can be solved independently. Provided that the number of different goal types can be kept small, this expansion of the system can be absorbed by running multiple threads, without a visible increase in the overall update latency. One final idea that merits exploration is to combine distinct graph components with distinct goal cell solutions. First, partition the navigable area into overlapping components. Next, seed each component with goal cells in the region overlapping its downwind neighbor. Each component is now solved independently, stopping at its designated boundary. Particles now use a high-level topology to select a series of components that allow them to reach a particular end goal. Within each component, they advect toward the goal located in its overlap region. Upon arriving in that overlap region, they transition to the next goal field, replacing the goal they've reached with the one at the other end of the overlapping component they've just entered. This design may present some practical implementation difficulties in that it significantly fragments the pool of data that the entities read from when they update their velocities. However, it also hugely shrinks the total size of each area needing to be solved as a coherent field. The solver can thus terminate earlier, visiting fewer cells, and each component can also be treated as a separate parallel task. I hope you've enjoyed this latest look into the development of Piste Perfect Ski Resort Builder. It may be a while before the game hits any kind of public early access, but if you want to keep up to date, then as the Hive says, like and subscribe. Also, check out the Discord link to join our server. Thanks for watching.